please fill out the attendance form. It's available in our chat room. All right. If you look at the e-learning portal, basically we are in week 12. All right. Earlier this week, I think yesterday, I've updated some of the materials inside the portal. If you go through from week, I think from week 6 up until week 11, you can find the lectures as well as tutorial, the online session. And you can also find solution for the class activity or the homework that I posted every week, except for week number 6, where I need to do it manually because I don't have the answer, the solution at the moment. Maybe later on I will, once it's ready, I will post it and inform of its availability. Okay, in week 12, what we try to discuss is that we try to learn about, not learn, like have a look back at Thevenin and Norton theorem. However, this time around, it's such theorem will be used in AC circuit analysis. And looking at the materials that I uploaded earlier this week, we have lecture notes, some of the examples, not some of the examples in the lectures, as well as usual, we have class activity. And later on Thursday, our tutorial session, we will have a look at this tutorial. And if you, I think it's better for you to have a look first at the tutorial question and try out some of the question, maybe one of the question, and later on we try to compare our answer in the tutorial section. All right, that's for week 12, and also some of weeks that from week 6 to week 11. And if you remember, the due date of assignment 1 submission already passed. It's last Friday. It was last Friday, and congratulations for those who managed to submit the assignment. But one more group, I think it's coming from group number 1, still in draft form. I think it's because all of the group member need to endorse the submission. So you need to endorse the submission in order for this status to be to become like this one, submitted for grading. So for group number 1, Hadif, Nakanishi, as well as Kayum, please take necessary action. Maybe you should, all group members need to endorse the submission in order to change this from yellow into green. So that's for our assignment submission. And next week, what I plan is I try to give you guys our last assignment number 2. It's also on multi-sim simulation, and you will be given with AC circuit this time around. So hopefully the procedure is the same. The group we try to keep the group as what inside assignment number 1, and you will be given maybe around 1 week in order for you to finish all the submission. All right. Okay, that's for assignment as well as e-learning portal. And if maybe later on, I would like to mention about tests, but I think we still have time. Maybe on Thursday, I will remind you guys on the test 2. All right, that's what's going on in e-learning. All right, as I mentioned earlier, this week we tried to have a look at Thevenin and Norton theorem. So these slides or this lecture slide lah, yeah, it's available in e-learning. And okay, we start. All right, I think we skip this one. At the end of the lesson, should be able to use Thevenin and Norton theorem in order to analyze AC circuits. This also a bit introduction from what we should expect. All right, this general step is basically what have been reminded to you time and time in order to solve or to analyze AC circuit. The first thing that you need to do is that you need to transform circuit parameters or the elements inside the circuit in frequency domain or in phase domain. For instance, like inductor, you need to convert it into XL value or its reactance value. And for capacitor, been converted or been transformed into XC value. And from there, you try to solve the circuit according to the given question. Or if you want to use any tools, you know, for example, Ohm's law, Kirchhoff law, Kirchhoff voltage law, and so on, up until this Thevenin and Norton tools. So you can use that techniques in order for you to solve any parameters or any problem inside the circuit. And if required, you also need to transform back into its time domain value. All right, that's for introduction. And basically for Thevenin and Norton theorem, I actually have only one slide over here. The rest will be the example. And basically, Thevenin and Norton theorem, we have been introduced before this in order to solve DC circuit. And the essence of Thevenin and Norton theorem is that we try to reduce our circuit from complex circuit in towards a more simpler circuit. For example, if you look at the figure at the right over here, bottom right, we have a linear circuit. Most probably this circuit will be a complex circuit. We have like series parallel connected resistors or any other passive elements such as inductor and also capacitor. And we try to simplify this complex circuit in this form. If you look at the one at the top, this is known as a Thevenin equivalent circuit, where we have voltage known as V Thevenin or VTH in series with our reactance, total reactance looking from the terminal over here. And the most important thing that for Thevenin is that voltage should be in series. And for a Norton equivalent circuit, or when we try to simplify our circuit using Norton theorem, what we are looking towards the end is that we try to find out what is the uh, Norton current, and also what is the value of Norton impedance, or Zn over here. And both current and the impedance should be arranged or should be connected in parallel. And here the difference between Thevenin and Norton is that if you look at the Thevenin, we have voltage over here, and the connection will be in series. And if you look at Norton theorem or Norton equivalent circuit, we should have like current in parallel with our impedance. And if you recall back the source transformation theorem, basically, if you have like Thevenin equivalent circuit, you can easily convert it into Norton equivalent circuit just by doing a source transformation technique. So it's like you can change into the other form easily if you have one equivalent circuit. Same goes to Norton equivalent. You can easily change it into Thevenin equivalent circuit by using source transformation. And the one that we need to remember, or we need to be particular with, is that both Thevenin equivalent and also Norton equivalent, if you look at the impedance value over here, ZTH and also Zn, is basically the same value. Okay, if you try to solve using Thevenin equivalent circuit, you would like to find out, or you would like to calculate what is the value of ZTH. And if you try to solve using Norton, you would like to you would like to find out what is the value of Zn. And basically Zn and ZTH is actually the same value. All right. So far, any problem?
All right, sir.
Okay. Okay, we move on into the first example, which is example 10.8. You can find this example in textbook as well. What we're trying to do here is that, according to the question, we try to obtain Thevenin equivalent at terminal A and B. This should be A. It's not 1. This should be A and B of that circuit. And what we should expect at the end of or towards the end of our solution, what we're trying to do is that we try to come out with a circuit which is look like this. Should erase this first. And put it this part as positive. You should expect a circuit, a Thevenin equivalent circuit, which is a voltage in series with our impedance. So this one is our ZTH, and this is our VTH. Doesn't matter whether you present VTH in phasor domain or in time domain, doesn't matter. It's the same. However, what I'm trying to explain over here is how to get these two parameters. And the way we get these two components, or these two values, VTH and ZTH, is by looking at the question, of course, and try to assess it using Thevenin equivalent circuit. Sorry, theorem, Thevenin equivalent theorem. All right, here's the solution. Okay, and of course, our main target is to get VTH and ZTH values and arrange that two components or two elements in series. So here, all right, looking at the question, the first one is that we try to get what is ZTH. And to get ZTH, basically you need to treat, there is a steps to in order for you to get the value of Thevenin impedance. Right? Now, the first step you need to do is that you need to identify where is the open terminal. The terminal, the open terminal according to the question is over here. We have denoted by A and B. And for the voltage over here, what you need to do is you need to treat it as V equals to 0. And since we put it as V equals to 0, means that this part should be a short circuit element. So from there, you should find out what is the value of Z from this direction. So this is the answer to, in order for you to get the value of Z, where the value of Z is basically according to this question, to this circuit, is basically these two, okay, these two connected in parallel, and also these two connected in parallel, and both are in series with each other. So you need to really identify or really like simplify the circuit in order for you to have a look at what's going on, or how do we calculate ZTH. So the best thing is that I always like put it like this. This is my A and this is my B. Terminal A and terminal B. So the way my main objective is to find what is the Z value coming from here. So from here, A I have E, and also I have 8 ohm resistor. I have okay, I have one here is, and another one over here. This is negative J6, and this is 8 ohm, and both are connected to terminal A. So this is terminal A, so I have two branches. One is 6, another one is what do you call it, 8 ohm resistor. And at the end of 8 ohm and also at the end of J6, it is short circuit, means that later on I have a short circuit connection towards here. Okay, and after that short circuit connection, or which is, this is D, I have another branches, where here I have like 2 branches, and these 2 branches is connected to B, and here also maybe this is a bit tricky to draw it. Okay, and if you look at from B, okay, from B, I have 2 components connected in parallel, which is, the first one is my 4 ohms, and another one is my G12. So later on I'll erase this one. If you look from this angle or from this sort of elements arrangement, it is easy to say that, okay, these two is in parallel, and as well as these two also in parallel, and we should combine these two together. So that's how we find what is the value of our total impedance looking from here. So that's what's going on in our solution. So here we say that ZTH is Z1 plus Z2, or the combination of these two parallel connected components. Right. Are you with me?
Yes, sir.
Okay. Right. Now we're done with our ZTH. Okay. The next one is to find out what is our VTH. Okay. Maybe I should change this one into a blue color. Okay. Now we try to find out what is our VTH. Oh, not attractive. Maybe here. All right. So for VTH, basically what you need to do is that you should keep this voltage as it is, and you don't need to treat it as a zero anymore. And the VTH is basically the voltage across these two open terminals. So basically we try to have a look, or we try to calculate at what is the voltage across these two terminals. And the way we calculate these two is that we try to redraw back our circuit. So according to the circuit that we have over here, we have like two branches. Oh, maybe you should draw it a bit nicer. And this is our VTH. And the bottom part, we have like this. Okay, this is our voltage. And this is element J, negative J6. This is what I don't like. Negative J6. This is the 4 ohms resistor. This is J12. This is like 8 ohm. And we try to find out what is the voltage across here. And maybe you should label it as like, this is your positive terminal and this is your negative terminal. And we would like to focus on this VTH. In order to calculate this VTH, you cannot simply like doing normal basic law like sorry. For example, maybe you would like to try Ohm's law. Okay, maybe you should use that, but you need to combine it with other tools. Here we know that the voltage is not, VTH is basically not the voltage drop across here. And this is not also voltage drop across here. And we cannot also say that VTH is the voltage from top over here up until this 8 ohm resistor. We cannot say that. But what we're trying to do is that we try to, maybe I change a bit the color over here. What we're trying to do is we try to come up with a loop equation, or using Kirchhoff voltage law to find what is the value of VTH. So we can either use this loop or this loop. So in order to use the loop over here, what we need to find is the voltage drop across these 4 elements. And please remember that this is an open terminal. If this is considered an open terminal, basically what we have over here, we just have a circuit which is looks like this. And maybe this is the voltage over here, voltage from the top and the bottom. Basically, what you are looking is this kind of circuit. So the first thing that you need to do is that you need to find out what is the voltage drop across the four elements, and later on work out what is the equation of Kirchhoff voltage law, either using this loop or this loop. All right, that's what happened in the solution. If you look at the solution over here, the first one is that it tries to calculate what is I1. And according to this diagram, I1 is denoted over here, I1. And this is denoted as I2, if I'm not mistaken. Let me see that. All right, 8 and J6, yeah, I1 and also I2 is 4 plus J12. Right, remember that if we have a parallel connected circuit, means that the voltage from the top over here up until this point, or at the bottom, same goes over here, from here up until here, we know that the voltage is this value. So same goes to the other branch, from this point up until this point, the voltage is this value. So that's why if you look at the solution, to calculate I1, the current flowing through this part or this branch, it uses this voltage and divided by the total impedance of this branch. Actually, what we're trying to do here is that we try to reduce the circuit to become like this. This is our I1 and this is our I2, and this is the voltage we are referring at. This is I1. Maybe we can label it as Z1. This is I2, and we can label this one as Z2. Okay, that is why in the solution we try to calculate I1 and I2 first. Why? Because from the value of current I1 and I2, we can simply calculate what is the voltage across here and also what is the voltage across here. Using I1, we can calculate voltage drop across negative J6, and using I1 as well, we can calculate what is the voltage drop across this 8 ohm resistor. Same goes to what's going on in the second branch. If you use I2, what you will get is that you can use I2 to get the voltage drop across here and also the voltage drop across here. Remember that this is an open terminal. And from there, you have all the information of voltage drop across these four elements. And if you look at the next solution or the next step, is that we try to apply KVL around the loop BCDEB. BCDEAB. I don't like that kind of notation. What I know is that I can use this voltage. Let's say I label that one as put it as red color. This is V1, V2, V3, V4. Okay. I can use the information of voltage drop across here. For example, if I am using this first loop, okay, If I start over here, I would say that negative V1 plus V2 minus VTH equals 0. And remember that you already calculated this value. Oh, sorry. You already calculated this value and this value just by rearranging this formula. This VTH value can easily be determined. If you look at using this loop, second loop, and if I start the second loop, maybe I change the color, change it into what else? This time I will use blue. Okay, if I use this second loop, I can rewrite my equation as, where should I, right over here. Okay, if I start here, oh my goodness. If I start over here, I can write, the first one is negative V3. Around the loop, I have positive VTH. And then I also have positive V4 equals to 0. This is considering that I'm looking at loop number 2. And this is basically for loop number 1. And comparing this first equation and this second equation, basically you don't need to work out the KVL using both equations. Only use one equation, but you can check your answer using the other equation. But here, it should give us the same value. If you calculate your VTH using this loop, maybe let's say this VTH is equals to what? VTH equals to 10 with the angle of, let's say, the angle of 0 degrees. So the value of VTH you find from this second calculation should also give you the same value as you see from the first loop. You should try this and prove that what I'm telling you now is, it should be the way we confirming our answer. Okay, if you look at the solution, it just use one equation over here. If I'm not mistaken, this is 4, negative 6, J6. Okay, it uses this, the first loop. So it uses this equation over here. But you can always check your answer using this, the second equation over here, the second loop. But the second loop is not necessary should be calculated in your answer, but it just for answer checking. And okay, this is also being given over here. You can either use this equation or no, this is the continuation from the first equation. All right, anyway, at the end, you will get your final answer of VTH. And remember that our main objective is to come out with a circuit consists of two elements connected in series, which is the value of our VTH as well as our ZTH over here. And this is our point or our terminal. This is the value of VTH, and you should write down what is the value of VTH later on in your solution. And this is the value of ZTH. ZTH equals to what? Blah, blah, blah. VTH equals to blah, blah, blah. Actually, this VTH is this value. And ZTH is the value over here, put it like this, this value. Okay, any questions so far? Any question from the floor? Still there?
No question, sir.
Okay, thank you so much for your response. All right. All right, let we proceed our example for example 10.9. But basically, I don't want to explain this one because this is something which is um not included in your assessment, but it's a bit tricky. It's a bit hard because we have like here, we do have dependent current source labeled as 0.5 IO over here. And maybe I try to go through the solution. If you have any problem, maybe you can come back to me and how, why is this, why is that, why is that. Oh, okay. Later on, maybe you can ask me about if you don't understand what I try to explain over here. All right. The main question here is that we try to come out with a Thevenin equivalent circuit. And remember that Thevenin equivalent circuit consists of two elements connected in parallel, sorry, in series. Okay. We have ZTH and also VTH over here. Our main objective is to find these two values and draw this circuit. And according to the question, find the Thevenin equivalent circuit. Okay, typo error. Should be from terminal A and B. Okay, it should be from terminal A and B. We return back to the solution. Right. In order for us to find out what is the value of VTH as well as ZTH, it doesn't matter whether you calculate VTH first and later on calculate ZTH. You can do that as well. You can calculate ZTH first and later on VTH, and or you can also calculate VTH and later on ZTH. According to the solution, it tries to calculate VTH first because VTH is the simplest or the easiest part. I mean, easier part compared to ZTH calculation because of this current source, dependent current source. Okay, we go through the solution. To find VTH, we need to apply KCL. And again, if you would like to calculate VTH, what you need to do is you refer back to the question, and the VTH should be the voltage across the said terminal, or in this case is terminal A and B. So VTH is basically over here. You need to calculate what is the voltage across these two terminals. And the way we calculate is that we try to apply both KCL and as well as KVL in order for us to calculate VTH. First one, we use KCL. KCL here, we focus on this point or this junction. According to this junction, we have a current over here supplied by 15 angle of 0 or 15. We have IO over here, and also over here. All right, this is tricky. And over here, it is basically 0.5 IO. Why? Because if you recall back the definition of open circuit terminal. So if this is open circuit terminal, means that the current over here is 0. And all the current flowing through this part is basically due to this dependent current source. So that's why you see here that sum of I in equals to sum of I out. If you look at the diagram over here, I in is basically 15 with the angle of 0. You can also write it as 15. And I out is IO plus 0.5 IO. 0.5 IO. So solving this equation, you know that IO is basically 1.5 IO. So that's why here we have IO equals to 10. Right. Solving this equation, you can get IO equals to 10. And using this information, okay, work out the KVL around this loop. Okay, around this loop. And if you look at voltage around this loop, it is basically given by the voltage over here, voltage drop over here, because current is flowing this way, it is drop over here. And let's say I put it as V, this is V1, this is V2. And of course, this is VTH. Basically, what's going on over here, we have like voltage across this element, and also we have another open circuit terminal over here. This is labeled as A, this is labeled as B, and maybe you have this as well, but it doesn't matter because we're only looking at the voltage across here and also voltage drop across here in order for us to work out the KVL around the loop. So this is labeled as VTH, and this is labeled, maybe just now we label it as V1, and it's V2. So working out the KVL around the loop, we can say that if I start my loop over here, down here, we have negative V1 plus V2 plus VTH equals to 0. And maybe you would like to find out what is V1, what is V2. Okay, according to the diagram earlier that we have, if we know what is the current flowing through here and multiply with these two elements, 2 minus J4, we can get this V1. In other words, I can say that V1 is actually coming from IO times 2 minus G4. And for V2 is, if you refer back to the original circuit, the current flowing through here is basically 0.5 IO. And to get V2, we can make use that current 0.5 IO and times the impedance value at the top there. Oops. We have a positive G3. And using these two definitions and put it in this equation, you can easily get what is the value of VTH. That is what happened in the solution over here. Okay. If you look here, we have negative IO times 2 minus J4 plus 0.5. Actually, minus IO is coming from here. We have negative V1. V1 is IO times 2 minus J4. And over here, we have positive V2. And V2 is given by 0.5 IO times 4 plus J3. And since these two is known, because IO, we can easily substitute over here. This VTH it can be easily calculated from this equation. Okay, that's why I would say that calculating VTH, particularly for this question, is a bit easy compared to what you will look later on for ZTH. All right, now we have the Thevenin voltage given by this. All right. And how about the ZTH? Okay, the ZTH, okay, to find ZTH, first we need to remove independent source. Okay, as usual, according to this diagram, this is a this is a current source, means that we need to treat it as a open circuit. So at the end, what we have here is that we have this impedance at the top there. We have another impedance over here, and we have dependent current source over here, and over here the dependent current source is treated as an open circuit. Okay. Consider this is our A and B, and you need to find what is our Z over here. Okay, this is what we should do. We try to remove independent source. Since this is a this is a current source, we treat it as open circuit, and this is Z1. Maybe I label it as Z1. This is my Z2. And what happened to this? Why don't we just since this is also a current source, why not we just remove that one as well? Remember that this is a dependent current source. For dependent current source, we need to treat it a bit different compared to the independent current source. What we need to do is that for dependent current source, we need to keep it intact like this and try to work out what is the ZTH from this direction. And since we keep it intact, means that we need to put some test voltage over here. Test voltage, or sometimes we put it as test currents also can. In this example, they put it a 3 ampere current source. This is basically the test source. I believe this is the first time you see how to calculate ZTH if the circuit have like dependent current source. So stay tuned, or please focus on what's going on over here. Okay, remember that this is dependent current source. We cannot just simply remove, or we cannot simply treat it as independent current source. We need to keep it intact in the circuit. What we're trying to do is that we try to put in a test source, and the test source could be voltage or current. In this solution, we put 3 ampere current source. Remember that this 3 is arbitrary value chosen for convenience. Means that you can use, for example, in this case, if you look at here we have IS equals to 3 with angle of 0. Maybe you can also put IS equals to 5, angle of 0, or you can put 10 angle of maybe 10 degrees. It doesn't matter whether, because this is a test source, you can put any value and any angle. But remember, you should put the test source as in order to make your calculation as convenient as possible. So don't put like 100 with angle of 65 degrees or something like that. It's not going to make your calculation easy. Although it's you can do that, but let's stick to the simplest way in order for us to calculate the value of ZH. And in this solution, maybe we stick with this value where we try to put IS as 3 with an angle of 0. So basically, this is the one that I mentioned just now. And the current direction is always pointing upward over here. Just put it pointing upward. And if you put it, if you put this one as a voltage source, you should put it pointing, the positive terminal should be at the top, negative at the bottom. This is also for your convenience. Basically, you can put it in any direction, but for your own convenience, because we know that the voltage over here that we would like to calculate is in this polarity. So according to this polarity, this is the suitable current direction. And also if you have like voltage source connected over here, test source, voltage test source, you should put it in this way of polarity. So here, number of divisible by sum of current leaving the node. Okay, here we try to apply KCL at where maybe we try to apply KCL. Okay, since this is basically can be neglected, okay, because this is open circuit. So the node that we are considering is that we have a node over here, which is located here. So now we know that this is I, call it I naught times 0.5, if I'm not mistaken. Ooh. 0.5 I naught, and the current over here, okay, we know that the current here is I naught, okay, and looking, if you connect this current source, means that we have a current over here as 3 ampere. Okay, if I draw back the current direction, I have, this is 3 ampere, this is 0.5 I naught, this is I naught, okay, and using Kirchhoff current law, I in equals to sum of I out. I can say that I in is 3 equals I out, which is 1.5 I naught. 1.5 coming from IO plus 0.5 IO. So we can get 1.5 I naught. Okay. Here, you can say that you can easily come up with the value of IO because only one unknown parameter in the equation. So IO is given by 2 ampere over here. And using KVL again, using KVL, we try to work out the KVL around this loop. So around that loop, you can say that this is the one that we try to calculate, and in this case, we put it as VS. Okay, if I'm not mistaken, this is the VS over here. And right, if we have a current flowing through here, means that this should be a positive, negative, and this part is positive, negative. Okay, the voltage Vs over here is the same voltage across this element. So Vs can be found, maybe I put it there, this one as V1, this one as V2. Okay, if I start here, negative V2 minus V1 plus Vs equals to 0. And basically V2 is I naught times Z2, and V1 is given by I naught times Z1. And the value of Z1 over here is 4 plus J3, and Z2 is negative 2 minus J4. And using these two values, you can easily get what is the value of your Vs over here. And why we need to calculate Vs? Because we will at the end use Ohm's law to calculate our value of ZTH. So we will make use this Vs and divide it with the current source that we provide earlier, and we can get our value of ZTH. In other words, we know the voltage and we know the current flowing through here. So it means actually Vs is also voltage across here. Okay, Vs is over here as well. So we know the voltage, we know the current, and we can easily find what is the Z from terminal A up until terminal B. So that's how we treat a circuit consists of this independent current source. Basically, this is a bit complex compared to what we seen if we have independent current source or independent voltage source. For dependent voltage or dependent current, we need to put a test voltage. We need to put a test voltage. Where should I put it? Okay, we need to put test source, either voltage or current. You can also use voltage over here, remember, and also you can put in this particular example, it's easier if we put current source over here. And never, by the way, this kind of question where involve dependent current or voltage source will be not in your assessment. Don't worry. This is for your own knowledge, I believe. If asked about how to solve dependent current source using Thevenin, so this is how we do it. So again, this is not inside your assessment. However, as electrical or electronic engineers, you need to know this knowledge. So this is some sort of extra knowledge for you guys. Hopefully, what I explained here, it's easily to be, what do you call it? You can easily get it based on what I explained over here. All right, that's for the second example. And finally, our last example before we end our session is about Norton theorem. Okay, in this case, what we need to come up with is that we need to come up with a Norton equivalent circuit. So remember that for Norton equivalent circuit, we should have a current source which is in parallel with our Norton impedance over here. And this is the terminal we are looking at. And maybe this is IN. So at the end, we try to come up with this kind of circuit, because it says in the question we need to solve current IO using Norton theorem. And we proceed with the solution. Okay, looking at the question, or looking at the circuit, we cannot find any open terminal in this case. However, the terminal is labeled as over here A and B. So again, if you have a terminal label like this and you have a component across the terminals, what you need to do is you need to remove this first. Remove this. Remove the elements across these two terminals, and you will end up with your circuit, which is arranged like this. Maybe I put this one as my impedance value. And this is my voltage source over here. Okay, let's say this is Z1, Z2, and this is my Z3. We should connect these two together. And this is our open terminal A and B. This is what you need to do first. Remove the elements across the said terminal. So after you remove it, the next thing you need to do, this is the first one. The next thing you need to do is that you need to find Norton impedance, or you can also start with your Norton current. According to this solution, it starts with the determination of the impedance first, and later on try to calculate IN. So we follow what's going on over here. All right. Now, how to how to calculate this Zn? Okay, remember earlier in the class, I said that Zn is basically equals to the value of Zth. And the way we determine the value of Zn and Zth also the same. What we're trying to do here is that we try to find out what is the impedance over here and label it as Ztn. Ztn, not Ztn, Zn. Not an impedance. Impedance from terminal A up until terminal B. So in our circuit, we have voltage source over here and also current source. And as usual, for current source, we will treat it as this one as open circuit, and this one should be treated as this one should be treated as short circuit. Maybe I should put it as short circuit. This is open circuit. Okay, these two need to be treated as its value should be equal to 0. So reducing from this circuit, you will come out with a circuit which looks like this. Okay, this is open terminal. And this is A and B over here. And we try to find what is the value of Z in that direction. Zn, we label it as Z. Remember that these two, okay, these two from this short circuit and these two elements, we can further reduce it to become like this. This is A and this is B. Z1. Again, this is Z1, Z2, and this is Z3. Okay. Remember that these two, we have short circuit over here. If we have a short circuit in parallel with our element, means that branches should be treated as short circuit as well. So, for example, like this, yeah. If you have a resistor, let's say this branch is short circuit. Let's say this, what is the value of R total over here? Total. Let's say this value is R. Okay, and R total is given by R times 0 divided by R plus 0, and R plus 0, this is 0 divided by R. What? 0 divided by R should be infinity, right? So infinity means that we have a short circuit over here. Not infinity.
It should be 0.
This should be 0. 0. I'm sorry. Oh, means that you're still there. Okay, this should be 0 as well. So 0 divided by a value means that the value is 0 as well. So 0 can be treated as a short circuit over here or over here. And since this is a short circuit, means that this part, maybe I change another color. This part can be neglected. This part can be neglected. So we end up with Zn over here is equal to Z1. And Z1 in this case is only this value. So that's why over here we have Zn equals to 5 ohm only. You don't need to calculate the value of Z in a complex way, because based on the definition of a short circuit, open circuit, we can easily find what is our value of Z just by looking or just by simplifying our circuit. All right, now that's for the Norton impedance. And for Norton current or IN, okay, recall back this circuit. For Norton, okay, for VTH, if you recall back, for VTH, we try to find what is the voltage across here, right? For VTH is a voltage across here. And for Norton current, what we try to do is we try to short circuit this element first. We try to make this, make these two elements as short circuit. Okay, short circuit, and the current is over here, IN. And based on the given values or given circuit connection, for IN, what our main objective is to find what is the current flowing through this short circuit element. So if you look at the solution over here, this is for Zn as I mentioned earlier. So this part has been short circuited. So we try to find the current over here, and the best way, according to this solution, is by using a mesh analysis. But basically, you can also use superposition theorem in order for you to get what is the current over here. It doesn't matter whether you use mesh or you use superposition. According to the solution, if you try to use mesh, between two meshes, or mesh number 2 and mesh number 3, we have a current source. And if we have a current source in between those two meshes, means that we need to treat it as a super mesh. So recall back super mesh. Super mesh means that we need to use both KCL and KVL. This is not like plus together, both KCL and KCL. So this is what happened in the solution. Okay. Notice that mesh 2 and 3 form a super mesh because the current source linking them from mesh number 1. So first we come up with a voltage drop across this first mesh given by this equation. And later on, if you look at the solution here, we try to apply super mesh theorem. And if you try to apply super mesh theorem, you need to work out the voltage or the voltage drop across this big mesh, combining mesh number 2 and mesh number 3. And also you need to apply KCL, where KCL at this point. Okay. From there, you can get your answer, and based on the equation, based on the solution that we have here, we have IN equals to basically the current over here, or the current I3, and after, okay, this is what happened. We have IN, again we have our parallel connected component of Zn, and we have open terminal like this, labeled as A and B. This is IN. Okay. Now, remember that first we remove the component we remove any elements that connected in across terminal A and B. So this is where after you find IN and also Zn, this is where we connect back our component over here. The component, maybe I label it as Z load, or maybe you can put it as Z, whatever Z you like lah. So this Z load is basically 20 plus J15. And in the question, okay, in the question, basically we try to calculate what is the current flowing through these two elements, or from terminal flowing through terminal A and B. So up until this point, we only get what is the value of IN. And to get what is the value of IO over here, we need to apply current divider rho. So this is what happened in this line or in this final answer in the solution. So we need to apply CDR. And if you notice that I didn't explain about this part and this part as well as this part, I would like you guys to try out and do some revision on what's going on in Super Mesh, basically. So that's why I leave you guys with without any explanation on this part and this from from this part up until this part. But basically, I've give you the hint where if you follow through the solution, it's quite easy to understand because we try to apply super mesh and try to apply this both KCL and also KVL analysis around the super mesh area. So I think that's finish up our example, the third example. Do you have any questions so far?
No, doctor.
Are you okay?
Yes.
Wait a second, I need to answer this one first. Okay, sorry for the interruption. Anyway, you have any questions so far? No? Can you
No.
follow what's inside this week lesson? And okay, I will leave you guys with what do you call it? You should try again this example, except for the second example. Maybe the second example is less significant in terms of assessment as far as I'm concerned. However, in for knowledge point of view, it's a knowledge that you need to know. But for example 1 and example number 3, I think you need to go through it back and have a look with the and recall back the tips that I showed you just now. Maybe it will be beneficial for you guys in order to really understand what's how to solve it, example number 1 and example number 3. Okay. All right, I think that's the end of our lesson. As I promised earlier, we should finish our class early today. Okay, for those who missed the link for attendance form, maybe you can have a look at our chat room for the link for attendance. And before we finish, normally I would like to ask you guys to do this practice problem. And if you cannot do this, the problem which involve which involve dependent current source, then that should be okay. However, for those for this the question which only consists of independent current source or independent voltage source, you need to master how to solve that kind of problem or that kind of question, because that is related to your assessment towards the end of this course. Maybe it will appear in your test too, or and again appear in your final exam. All right, please have a look at this homework. And as usual, we try to submit it before Friday. No, before Saturday, maybe Friday. And I think that's the end of this week lesson. And our next topic will be, I think, easier than what you've seen in AC analysis in previous week, because I try to introduce you guys with AC power, which is a bit easier compared to what you've seen in the past few weeks. So in AC power, as I mentioned earlier in, I think week number 1, I mentioned this part, where in DC circuit, you only know about power is P and the unit is watt. However, in AC powers, you will be introduced with reactive power, apparent power, and active and reactive, of course. And also, if you combine this active and reactive power, it will come out as a power which is known as a complex power. So basically, active and reactive power is the real power and also the imaginary power. I mean, if you consider it is a complex number. All right, and later on you will be introduced with a power triangle, and we try to get to know what does it mean by power triangle and how what is the pattern of the triangle. Of course, the triangle have it's a simple triangle. We have 3 edges. We have it's a triangle, but we need to explain. I mean, we need to what we call it, make use of the triangle in order for us to get to know the information of power in our circuit. All right, with that, I think thank you for your attention. And oh, no. Sharing first. Okay, as usual, please turn on your webcam so that I can have a look at your face, whether boring or whether really understand. Anyway, I hope that on Thursday you managed to join the tutorial session. I think tutorial session is more interesting compared to what we have today. So make sure you present yourself during the tutorial session, and please cooperate well, every time we have tutorial, I will try to get answers from you first, and later on we try to discuss. So try to cooperate, and if you want to try the tutorial question in advance, maybe you can have a look at e-learning portal to get the question first. Okay, please turn on again. All right, I'll try to snap your picture. Okay, smile. Right. Anyway, thank you so much for your attention. We will meet again on Thursday, 11 a.m. All right, with that, Assalamualaikum. Thank you so much for your attention. Stay safe, guys.
Assalamualaikum, Doctor. Have a good day.
Thank you, Raja.
Thank you, Radha.
Jika itu akan berjalan hati.